Welcome back everyone to 264A Automated Reasoning, and this is our lecture 4. What we'll do today is we will continue with our discussion on satisfiability, in particular solving satisfiability using search. What we'll do initially is lead the way to the DPLL algorithm, which is based on depth first search, and then what we'll do is discuss some further advancements that came after that, which led to what people today call modern SAT solvers. This is all in your chapter 3, and as before, chapter 3 actually have a lot more material than what we will cover in class, so you will need to use the lecture as a guide for what material we will be going over. I'm going to go ahead now and turn my camera off and head back to the whiteboard to get started. So let's go ahead and do that. I'm going to start by putting up an example that we ended up with last time and use that to motivate our discussion. All right, so this is the example that we used last time. We actually had the algorithm that we called SAT2, which is this guy, and this was an implementation of depth first search to be able to find a truth assignment that satisfy the formula. We had the base cases, which look for a knowledge base that has been satisfied or one that is inconsistent. And then we had the two recursive calls here, which are basically branching on either a variable or its negation. And then we showed this concept of a termination tree, which tell us what kind of or what part of the depth first search tree that was explored by SAT2. And in this example, which starts with this particular knowledge base, has 3 clauses. We see that we started by setting A to true, B to true, and then C to true, and then we found a contradiction. So what we say backtracked and tried C false, and then we tried D true, and that was a contradiction, and then we tried D false, and finally we were able to satisfy the formula, and we found this particular truth assignment which satisfies the formula. And the idea that we ended up with is that if we add unit resolution to this process, then we can make things better. And in particular, we said that after setting A to true, and therefore our knowledge base at this point will be this guy here, we said that we could have run unit resolution at that point, and that would have terminated the search. So we have the unit clause B, and we can resolve this guy with that clause. And at that point, we will end up reaching the unit clause C. And then if we resolve this one with that guy here, we will end up having the unit clause D. And we already had the unit clause B. So effectively, and we have already set A to true. So at this point, you will see that under these variable setting, A equals true, we inferred B is true, C is false, and D is false. And that would basically simplify the knowledge base to true in this case. And we would have terminated the search at that particular point. So what we're going to do next is integrate this idea of unit resolution in the algorithm, and as a result, we will get what is known as DPLL. But what we will do is do it in a specific way. We will introduce a new function that does unit resolution, which I'm going to go over next, and then we'll show you the code for DPLL, which would look a little bit different than what's going on here, and we'll see why. So let's go ahead and do that. And I'm going to put this under the label of DPLL. And we can refer to this as depth first search plus unit resolution. Okay, so the first thing is we will have this new function. We're going to call it unit resolution, and it will take a knowledge base delta. Now, this guy will return 2 things. So first is a set of literals I, and then it would return new knowledge base del. So let's explain what these guys are, and then we'll take a concrete example. All right, so what this function does, unit resolution, it takes a knowledge base and it applies unit resolution to the extent that can. So this is what we refer to as clausing the knowledge base under unit resolution, applies all possible unit resolutions. And then it would return a set of literals that were either present initially as unit clauses in delta or that were derived by unit resolution. And then it will condition the knowledge base delta on these literals and then return the results as gamma. So let's take a concrete example. Here's one example where delta is basically the following clauses, and you want to help me out with this one. So I have not A, not B. This is one clause. And then I have B, C. And then I have not C, D. And then I have the unit clause A. Okay, so this is a knowledge base that have 4 clauses. And I want you to tell me what would I be in this case and what would gamma be in this case. And I will get this started by telling you that I will have this literal A, the positive literal A, because remember, it's a set of letters that were either present, so this was already present, and then what you need to add to that is what other literals get derived by unit resolution. So I started I for you as a set, and you can type, okay, so someone is already writing that I should have, in addition to A, I should have not B and C and D. These are the literals, 3 of them that gets derived by unit resolution. So let's see. So if you resolve this guy with this, you actually conclude not B. Now that I have not B, I can resolve it with this guy, and then I will get C. And if I resolve C with that guy, I will get D. So actually this is correct here. And now the question is, what is the knowledge base that is returned, right? Remember, according to the definition, I'm going to take this guy, delta, and condition it on I and return that as a knowledge base. And I'm also getting the answer that it will be this guy here, which is true. All right, and that's again correct in that particular case. So that's what I'm going to get in this case. Okay, let's take another example here, which is the knowledge base in this case is the following. I have delta equals not A and not B. That's the first clause. And then I have B, C, and then I have not CD. And finally, I have the unit clause C. Okay, now I'm not giving you any help. You're going to go ahead and tell me what is the set of literals I returned and what is the knowledge base. Okay, folks, what are the literals that are returned in this case? You can type this to the chat box. Remember, those are either the literals that appear as unit clauses originally or that are derived. And I'm getting a couple of answers that should be C, D. C, because it's already present, I can resolve this with that, I get D. And there is no more unit resolutions in that particular case. Okay, then you know what's coming next. What is the knowledge base that I should return? Remember, that is this guy conditioned on these guys. So what happens in that particular case? What is the knowledge base? And someone is typing that that should be the clause not A and not B. Remember, if this is setting C to true, setting D to true, then this clause gets subsumed, get removed. This is the same, and this the same. All of these guys have literals that end up being true. So those guys go, and I'm left with that particular guy. Okay, so now that we understand what unit resolution does, this particular function here, we're going to use it as an aid. And now I'm going to show you the code for what we will call DPLL. Which is depth first search that is augmented with unit resolution. But you will see that the code that I'm going to show you look a little bit different from what you may have expected as far as augmenting SAT2, and then we will talk about that and see why is that the case. So let me get rid of this first here. All right, so this is the code, and we'll need to go over it. And what I have here is DPLL. It simply takes a knowledge base in closal form, and it either returns a set of literals or fail. If it is a set of literals, then those would be a partial variable assignment that is guaranteed to satisfy the formula. All right, so as we mentioned, this would represent in general a set of worlds. Now, here's what's going on. The first thing I'm going to do is I call this unit resolution function that we just talked about, and I'm going to get the modified or simplified knowledge base gamma, and I'm going to get the set of literals. And then I have my two base cases. So the first base case is if gamma is already basically satisfied. So it's been reduced to true, as is going on here. So in that case, I simply return these literals. The other base case, if the empty clause appears in gamma, that means unit resolution has discovered a contradiction. So I would return fail in that case. And now here's what happens. So look what I'm doing here. I'm choosing a literal in gamma, and then I'm doing case analysis on it. I'm adding that literal to the knowledge base as a unit clause, and then I'm trying. And if that works, then what I would return is those guys and the result of the recursive call. I union them and return them. If that fails, then I'm going to try adding the negation of that particular literal as a unit clause and do the same thing. If both of these fail, then I simply return fail in that particular case. Now, you may realize here that there is a significant departure beyond adding unit resolution to what we had with SAT2. There are actually two other differences beyond unit resolution. And can someone actually say something about that? We did two major things that were different from SAT, and they center around this step 4. If you remember, and I'll give you a hint, if you remember in SAT2, what we had is we had our variables ordered like P1, P2, Pn, and then we went ahead and started trying the variables P1, P2, Pn, and then whenever we tried something like P1, we said, let's try it being true, then try to being false, and then we did this guy, and then true, and then false, and so on. Okay, let me see. Someone is saying there is no variable ordering as before. Excellent, correct. So basically, when we did SAT2, we had a fixed variable order, and we were following it. So under this particular branch, we were going P1, P2, P3, and then when we went to another branch, again, we were doing P1, P2, P3. And in this particular case, we are not doing this. When we're getting to this point, I'm just saying pick some literal from that, try it and try its negation. And that turns out to be very significant in terms of performance. What this means is I may be trying things in different orders depending on the branches. And this is known as, now you will have to use some kind of heuristic to make that choice. Here it's just left arbitrary, but this is known as a variable ordering heuristic. And people have really invested significantly into this. In fact, there was a time a while back where you will find paper after paper, people trying to actually come up with heuristics for choosing variables to what we would say split on next. So when you're trying, L and then not L, we call that splitting. Sometimes they also call them variable splitting heuristics. We'll talk about this later, perhaps actually on Thursday. Now, there's also one more difference here, which is perhaps even subtler than this. And let me see if someone actually, someone mentioned. So I see evaluates P, then not P. For SAT2, we said a good variable ordering can solve faster. Yes, so this basically leaves the opportunity when we say choose a literal according to some heuristic. So the idea is that you will employ a heuristic to that choice. Okay, this one is a little bit subtle. And remember, we are not picking a variable. We're picking a literal. So if you picked a variable P, then this would be try P and then try not P. but we're picking a literal. So when you're picking a literal, then you may have picked P, and then you would try P and not P, but you may have picked not P. In that case, you would try not P first and then P second. So the idea is that we are not basically committing to trying to set a variable to true first and then to false. Sometimes we may, when we pick a variable to split on, sometimes we try false, true false, and then sometimes we try false true. And that can also have a significant impact on performance. Sometimes people call this as a phase selection heuristic. All right, which is, what do? You try the variable true first, or you try false first. What value of the variable do you try first? So this algorithm, beyond integrating unit resolution, it also allows you to integrate a variable ordering heuristic and a phase selection heuristic. So, okay, this is what I wanted to say about DPLL. And now we're going to go and show an example that illustrate a major place where one can improve further. And that example that we're going to show next will motivate two new major concepts that once we motivate, we will see how to address. And once we address, we'll end up reaching what people call modern SAT solvers. So before we go ahead and do this, let me just take a quick look here to see if there are any questions. Is it DPLL return assignment? SAT2 returns. Right, so this would return, just like SAT2, it would return a partial variable assignment. No, these are not the same things, because this particular L is the result of doing DPLL while adding this literal, but this particular L is the result of adding that particular literal, which is the negation. Okay. So let's go ahead and look at the next example. I'm going to put this under what is known as chronological backtracking. Yeah, this is going to be a substantial example. We're going to spend quite a bit of time on a number of fronts. I'm going to start by putting this example. It is a knowledge base. And then I'm going to show you the termination tree. I'm going to put the termination tree for that example. And then we're going to make a whole bunch of observations, which will motivate quite a bit as far as the new concepts that we will address. All right. So what we have here is a knowledge base that have 7 clauses. And we have the variables A, B, C, and then X, Y, Z. And I'm going to assume in this particular case that I'm doing depth first search using these particular variables in that particular order, A, B, C, X, Y, Z. And then that I'm going to be trying true, false, and then true first, and then false second. So if we do that, you will see here the termination tree. I went ahead and set A to true, and then tried a whole bunch of things. So for example, A true, B true, C true, and then I set X to true. And at that point, unit resolution will actually detect a conflict. You can see that. You can try it. In fact, we will see it next. And then look what happened. When unit resolution discovered a contradiction in this case, I went and then tried X equals false. And then unit resolution will also detect a contradiction in this case. And then I would backtrack. We would say I would backtrack to C and then try the other value for C. And then at this point, nothing. Then I try X equals true. And then unit resolution again detect a contradiction, and so on. So this process of going back to the previous level, like when I was here at X, and I tried both true and false, and both failed, I went back to the previous level and I tried the new value for F. And then when I got nowhere here, I went back to the previous level and tried the other value of B. That's known as chronological backtracking. All right. And this is to be contrasted with what we will call non-chronological backtracking, or sometimes people call conflict-driven backtracking. We'll see what that means in just a little bit. If you look carefully through this example, you will actually find out that when you got here and reached a contradiction by unit resolution, the variables B and C had nothing to do with that, right? So they were actually not related to why this is happening. And you will find that the real culprit here is that you have set A to true. Now, if you knew this, then there is no point wasting your time and going and trying the different values of C and B. You should basically go all the way up and try to reverse the value for A. Now, if you do that, that is, if you get to this particular point and or some of these other points and then get a contradiction and say, hey, what is the reason for that contradiction? And then you say, it's because of A. And then you go and jump all the way there. Then you will be doing what we would call non-chronological backtracking. Now, the question is, how do you do that? Okay. So this is something that we will discuss. And there is a very specific, sharp technique, nice actually, and relatively simple, that allows you to actually figure out how to jump to earlier levels. Now, there's another concept, which is now will look very different from this one, but they're actually pretty connected. And this concept has to do with the fact that unit resolution is not complete, right? So in this particular case, adding A true to this knowledge base leads to a contradiction. However, unit resolution could not see that. And if you are doing real resolution, full resolution, you will discover that. So when you add, if you add the unit clause A to the knowledge base, then you'll be able to come up with a contradiction. But unit resolution cannot discover that. And even after I added B true and then C true, still unit resolution is not able to see a contradiction. Only when I added X equals true, that unit clause, that unit resolution was like, okay, I can discover a contradiction. Now, there is this notion of an empowering clause for unit resolution. So, okay, this is first concept, this is second concept. And let's get rid of this guy. So there is the notion of an empowering clause for unit resolution. What does that mean? This means a clause that is implied by delta, all right? So it is something that is implied by delta. But if I were to add it to delta, then unit resolution will start being able to see things that it could not see before. And in this particular case, an example empowering clause is actually the following: not A or not X. This is a clause that actually follows from delta. It is implied by delta, right? So if I add it to delta, I'm good, right? I'm not changing the content of delta. However, if you were to add this clause to delta, then the minute you go and set A to true or add that unit clause that correspond to the positive literal A, then at that particular point, unit resolution will be able to see a contradiction, right? It's a very important concept. And the question is, well, how do I discover these empowering clauses? And how can I use them to enable unit resolution to see things that it could not see before? And it turns out that these two concepts are actually connected. That what we will do next is show you a technique that can be used to discover these clauses. More generally, people call these learned clauses. We'll look at a technique that allows you to discover or to learn clauses. And then we will see that if you use that technique in a particular way, then it will also help you discover where you should backtrack to, and therefore you end up implementing non-chronological backtracking. All right? So that's what we're going to do next. But let me just again tell you, and maybe let's see, should we do this here? Again, try to do this at home. Try to take this clause and add it as, let's say, number 8. And so not A and not X. And then try to see what happens when you also add the unit clause A, which correspond to this. So try to do two things. First, with the presence of 8, and now you have this, run unit resolution. You should be able to detect a contradiction. And then try to do that without having this guy. Try to run unit resolution in this case, and you will not be able to see a contradiction, okay? Now, let me just stress one more thing. The notion of a learned clause is not that specific. Learned clause typically refer to the fact that I discover some clause that's implied by the knowledge base and I add it. The notion of an empowering clause for unit resolution, that's more specific. So I'm not just talking about any learned clause. I'm not just talking about a clause that's implied by a knowledge base, but I'm looking for one that is empowering to unit resolution in some very precise sense. Now, we're going to leave the notion of empowerment at this level, at this intuitive level, that it is a clause that allows unit resolution to do more, but we're not going to define it formally. That's a little bit more advanced. You will have pointers to that if you need. Okay, so what we're going to do next is go ahead and show you how do you actually discover these learned clauses, and then how can you use them to even decide where to backtrack to, and then we will have all of the ingredients that we want to put together and then show you how modern SAT solvers work. And what we're going to do here is we're going to put this under the term implication graphs. So this implication graph is a tool that we will introduce now, which allows you to learn these clauses, discover these clauses that are implied by the knowledge base and that you can use to empower unit resolution. And as we will see, it will also gives you a hint or a strategy for doing non-chronological backtracking. Now, what the implication graph does is, and I'm going to go ahead and draw one for you. And it is something you can think of it as a data structure that is maintained to keep track of how resolutions are applied and how we actually got a contradiction. So let me draw one, and then we'll explain what it is. So remember, in our previous example, we went ahead and set A to true, and then we went ahead and set P to true, and then we got C equals true, and then we got X equals true. This corresponds to that particular branch where I was going like this. So that particular place, right? So these were all true, true, true. And then here I got a contradiction, okay? And of course, there were other branches for the tree and so on. Now, this implication graph is trying to capture the state at this particular point. What happened here? So in this case, these were the decisions. I'm going to call these decisions. We're going to make a distinction between things called decisions and implications. So these guys were all decisions because I had a choice and I made these guys. And then what we're going to also talk about is the level at which a decision is made. So this was at level 0, this was at level 1, 2, and 3. Remember, we talked about these being level 0, level 1, and so on. And this is 2, and this is 3. Now, anytime unit resolution perform a step, we're going to capture it in this notion of a graph. So what we're going to have here is the setting y equals true, and that setting is the result of taking this unit clause and that unit clause together with the clause 3. So if you look at clause 3 says not A, not X, Y. Now that I've set A to true and I set X to true, those guys get resolved. So I end up concluding Y is true. And this is what this is doing. I concluded Y is true, and then I had that using clause number 3. Now, this is called an implication. It's not something that I decided like these guys. It's something that got implied by unit resolution and my decisions and other things. Okay, now we're going to go ahead and continue with applying unit resolution and capturing that in the graph. So let me see. I'm claiming that we should be able to conclude that Z equals true, but I want people to tell me what clause could have been used for that. So I'm doing here Z equals true, and based on what, so I already decided that A true, B true, C true, and X true. And using unit resolution, I already concluded that Y equals true. And now I'm claiming that I should also be concluding that Z equals true. And people are saying that is clause 5. Indeed, clause 5, this and that together with clause 5 will actually allow me to conclude that Z equals true. Okay, very good. And now we can get a contradiction. So I'm going to put here a contradiction, which is this guy. And the question is, what is the clause that I can now use to get a contradiction? Remember, I've already inferred that Y equals true and Z equals true, and I should be able, and a whole bunch of people are saying 7. Look at 7. I'm already, this says A have to be false, or Y false, or Z false. Now I already assume that A is true, and I concluded Y is true and Z is true. So together, these guys actually allow me to get a contradiction. So I'm gonna put this guy like that, and this would be 7, 7, 7. Okay, there was a question earlier. What are the clauses that were involved in a contradiction? Now you see the example. Okay, we're missing one more thing from this implication graph. So we just did an implication graph. And the thing I need to add is we need to keep with every decision, like these guys, or an implication, we need to keep the level at which it was either assumed or derived. So level 0, 1, 2, 3. What do you think I should put next to this guy? What level I should put next to this? 3. Exact. So this was done at level 3. And similarly for this guy, all of these were actually implied, or these implications were at level 3. Very good. Now we have our implication graph. So here's the implication graph. So again, implication graph is somewhat of a data structure that shows us how we got a contradiction using unit resolution. Now we're going to see how useful this thing is and what we can do with it. It will allow us to see through why did we get a contradiction and what really contributed to a contradiction. And in particular, it will allow us to learn clauses. So the concept here is that of what we call a conflict set. Let me write it here, a conflict set, which is effectively a set of literals that if I add to delta, will get a contradiction. Okay, so it's a set of literals that if I were to add to the knowledge base, I'm guaranteed to get a contradiction. Now, if it turns out, for example, that A equals true and X equals true is a conflict set, what can you conclude? If this turns out to be a conflict set, what do I conclude now? I conclude that the negation of that must be implied by the knowledge base, correct? By the refutation theorem. So if this turns out to be a conflict set, then the negation, which is not A or not X, is what we will call a learned clause, or is a clause that follows from delta. You guys get it? So now I'm going to use this particular implication graph to identify conflict sets. And each one of these conflict sets will end up being or leading to a learned clause. Now, we're going to see that this guy, for example, already allowed me to discover 3 different conflict sets and therefore 3 different learned clauses. We'll do this now, but when we get back, we'll take a closer look at these notion of learned clauses and make a particular choice there, which will matter. Okay, guys, so here's the idea. How do I get a conflict set? If you look at the implication graph and do a cut in the graph that separates the contradiction from the decision, every such cut will allow you to actually identify a conflict set. So let me show you some cuts here. Here's one particular cut. All right, so the first question is, we need one criteria for it to be a valid cut. I need on one side to have the contradiction, this guy, and I need my decisions to be on the other side, and that is satisfied. Now, the edges that I'm cutting here correspond to variable settings. So in this particular case, what's happening is that I have A equals, okay, let me use a better color. I'm having, in this case, A equals true and X equals true. That's the variable setting that's defined by this cut, and that is a conflict set. You know now for sure, if you add A equals true and X equals true, you add them to the knowledge base, you are gonna get a conflict or a contradiction by unit resolution. Now, let's try another cut here. And how about this guy? Let's do it in green. How about this guy here? That's a cut. Now, tell me, what does this define? What is the conflict set that's identified by this particular cut? Can someone type that? Okay, someone is writing A equals true and Y equals true. Okay, that is another cut. Excellent. There is a third cut that we can do here. And let's do that. And then we're getting basically to our break. So here's the third cut. This cut also separates the decision variables from the conflict. And in this case, there are 3 variables involved in this particular cut. And that is A equals true, and Y equals true, and Z equals true. So that is also another conflict set. So each one of these defines a conflict set and therefore define a learned clause. So if I look at the first cut, and we saw this here, and I take the negation of these guys, then I get the clause not A, not X. This is implied by the knowledge base, and this is actually a learned clause. Now, if we look at the second guy, we're going to get not A, not Y. And now this is also a learned clause in the sense that it is implied by the knowledge base, and I can go and add it, and the last one as well. So we're at our break time. Let's take our 10-minute break, and then we come back and we finish the story. There is more to be squeezed out of this guy, and then we will be ready basically to put everything together and show you how modern SAT solvers work. And then you'll be surprised even once more. Okay, back at 11. Thank you.